Hello, hello, hello. In this worked example, we're going to consider what happens when I weigh myself in Wellesley. What will the scale read? Well, it depends on a number of things. It certainly depends on my mass uh, and the value of G, but the issue is that Wellesley is located on the Earth, as you know, sort of around this blue dot, and the Earth is rotating. And so the Earth is technically not an inertial reference frame. We are accelerating due to the Earth's rotation. And we want to consider what happens when you make a measurement inside a rotating reference frame. And it's sort of at the center of the joke here in this XKCD, which you've seen on problem set number 3. The physics that we have to deal with is the physics that was dealt with in the what's the big idea on the equivalence principle. And you remember in that What's the Big Idea, we considered a character named Al who was riding in an accelerated reference frame. And the main conclusion was that the reading on the scale, I guess the reading is here, would be the apparent weight of Al, which depends on his mass, the value of G due to gravity, but also the value of the acceleration of the reference frame. And so this is the formula for how we calculate the reading on the scale, and we can apply that formula to figure out what I weigh in Wellesley. And more generally, we can think of things as if the value of G in Wellesley is not just due to gravity. It's as if there's an effective value of G, which is just the actual value of D minus G minus the acceleration of the reference frame. So this is another very useful formula for thinking about how the world appears when you're making measurements in an accelerated reference frame. So to think about how these formulas apply in some real situations, let's first, before we get to the rotating Earth, let's take a first example of another rotating object, the rotor. The rotor is a classic amusement park ride, which is illustrated conceptually here, and this is an actual picture of the rotor in action. And in the rotor, you enter some sort of rotating you enter a room, it sort of looks like a drum, and the drum eventually is going to rotate. But initially, you're standing on the floor, and then the drum starts to rotate about this axis. And after you're up to speed, the floor just disappears. There's some mechanism that pulls the floor out from under you, and you're left um, going around in circles, but you don't fall. And then the question is, why not? Let's explore the physics of the rotor and see how it relates to these formulas about what happens in rotating or accelerate, or more generally, in accelerating reference frames. So once the drum is rotating, the effective value of G, it's going to feel as if there was a gravitational acceleration that is given by uh, G minus A. And if we use the XYZ coordinate axes, which I've shown here, G points in the minus Z direction. So uh, the actual value of G is minus 9.8 meters per second squared times K hat. And then the acceleration of the reference frame we know is V squared over R, and the acceleration points in the n hat direction, that's radially in, but then there's this minus sign here, which switches the direction of the second term to point outward. So the situation is shown in the drawing here. G effective has a component in the minus k hat direction, but also a significant component that points uh, in the outward direction, or I guess we would call that the minus I hat direction. So the effective G is pointing outward. And So it's as if in this rotating reference frame, it's as if there's a gravitational force proportional to your mass and g effective. So it's like there's a gravitational force uh, pointing in the direction shown by the red arrow. And then if you ask, well, why doesn't the person fall? Well, if you draw a free body diagram for the person, there's a contact. The other force in the problem is the contact force between the person and the surface of the drum. And part of that contact force will be a frictional force, which can point upward. And that frictional force can overcome the component of the effective gravitational force. There is a downward component, but the frictional force can offset that and keep the people from falling. So that's how the rotor works. Now let's use the same physics to think about what happens when I weigh myself in Wellesley. So every morning I get up and I weigh myself. And what I'm really interested in when I weigh myself, of course, is knowing what my mass is. And in order to really know what my mass is, I take the reading on the scale, and then I have to know how to convert the reading on the scale to get my mass. And what the arguments that we have given show that my thing that my scale will measure is my apparent weight, which depends on my mass and the magnitude of this quantity, g minus a, where g is the acceleration that's due to gravity, and a is the acceleration of my reference frame. And because Wellesley is located on the rotating Earth, we're in an accelerating reference frame, and that's going to affect, it's going to have some effect on the reading that my bathroom scale measures. Now, to answer this question, let's first start off with a somewhat simpler geometry. And what I'd like to consider is suppose I go visit uh, my Aunt Sacy, who is from Ecuador. And Ecuador is located right there, right on the equator. Aunt Sacy grew up in Guayaquil, and that's very close to the equator. Uh, so let's calculate what things would look like in Guayaquil. So if I'm standing on my bathroom scale in Ecuador, Ecuador is, as we said, located right on the equator. So when you're in Ecuador, you are, due to the Earth's rotation, you are traveling in uniform circular motion around a circle of radius r sub e, where r sub e is the radius of the spherical Earth. And that means that when, due to the Earth's rotation, you are in an accelerated reference frame. We know that your acceleration when you're in uniform circular motion will be given by your speed squared divided by the radius of the circle in which you're moving. And the direction we'll call, as usual, n hat, which is the a direction pointing radially inward towards the center of the circle. And we can express the speed of an object that's going around in uniform circular motion in terms of its angular speed, which we've called omega, times the radius of the circle in which it's moving. And remember, let's get some numerical values here. The angular speed of the Earth is measured in radians per second. So the angular speed of the Earth, we go through 2 pi radians of rotation in one day, and one day is, as you know, 86,400 seconds. So if you plug this into your calculator, you find out that omega has a value of 7.3 times 10 to the minus 5 radians per second. And that means the acceleration due to the rotating Earth, I can rewrite v squared over r times n hat. Just can write v as omega r. So this is equal to omega squared times r sub e times n hat. And if you plug in values this value for omega, and then the radius of the Earth, which is 6.4 times 10 to the 6 meters. The numerical value that you come up with is this 0.34 meters per second squared. And again, the direction is n hat, pointing radially inward. So the reading that I'll get on the scale, if I'm making the measurement in Ecuador, my apparent weight will be my mass times, again, the magnitude of G minus A, and that's my mass times the magnitude G in this figure here. G, when you're standing in Guayaquil, Ecuador, is pointed towards the center of the Earth, so that's in the n hat direction. So G is equal to 9.8 meters per second squared times n hat. That's the G due to gravity. And now I have a minus A here. So minus A, and the minus sign will right there. And so we're going to subtract off from 9.8 this number 0.34 meters per second squared times n hat. So the effect of our spinning on the Earth, you see, is to reduce the magnitude of this vector, because I have 9.8 minus a small number. It's not a huge effect. It's just a few percent, or I'm sorry, a fraction of a percent, three tenths of a percent effect. But it's a measurable effect nonetheless. If you've got a good bathroom scale, you might be able to detect the difference between when you make the measurement in Ecuador versus, say, if you were standing at the North Pole. If you're standing at the North Pole, then your velocity, omega, is the same, but the radius of the circle that you're moving in goes to 0, and you're not in an accelerated reference frame when you're at the North Pole. And that must mean that the apparent weight that you get is just equal to m times g. Okay, so the last question, which we'll just answer sort of qualitatively, is what about if you weigh yourself in Wellesley? Wellesley is sort of intermediate between the North Pole and the equator. We are located in Wellesley at a latitude of 42 degrees or so above the equator. And that means we're going around in a circle whose radius that is a little bit less than the radius of the Earth, and you can do the trigonometry to figure out how much less. But also significantly is the direction of our acceleration due to this rotation points inward towards the center of the circle that we're rotating in. So that blue arrow there represents the direction of our acceleration due to our uniform circular motion. And the G due to gravity points towards the center of the circle along this purple arrow. And this picture sort of exaggerates the effect. The acceleration, the length of the blue arrow is a lot shorter than the length of the purple arrow, as we just calculated. So when you go to calculate G minus A, you're going to get something which I will attempt to draw sort of in green. It's going to be tilted just a little bit this way. Away from the purple arrow. And so it's a little bit, the geometry is a little bit complicated, but the qualitative effect is that your apparent weight is going to be different, and its magnitude is going to be somewhere in between the magnitude that you have when you're standing at the equator and when you're standing at the North Pole. So that's it for this worked example. Hope to see you again soon. Bye bye.